Hello and welcome to a new video on second order differential equations. So in today's episode we'll be discussing and laying down the foundations on how to solve second order differential equations. I absolutely recommend seeing the first episode to it, first order differential equations, because that will make things a lot easier and more beneficial to you. Now, what we're going to be discussing is the difference between homogeneous and non-homogeneous differential equations and which cases we'll need to consider in solving into a general solution and maybe into a particular solution. So we're just laying down the foundations as such. So let's begin. Let's begin with homogeneous equations. What is a homogeneous equation? So I will give you three examples, and then I want you to see if you can spot the difference. It's going to be easy to spot it, but I want you to see why I do it as such. Okay, let's begin. Let's consider an example of d2y by dx squared, 2dxy plus 5dy by dx plus 3y equals 0. Now, this is an example of a homogeneous equation. A homogeneous equation is where this differential equation is equal to 0. So, I want you to just follow the steps and then see where we get from here. So, if we form this into a quadratic equation, so we have 2m squared plus 5m plus 3 equals 0. Okay? Now, when we solve this, we will get 2m plus 3, m plus 1 equals 0. So, our solutions for m is minus 3 over 2, and m is equal to minus 1. So, what we can say is that the general solution is equal to y is equal to ae to the minus 3 over 2x plus be to the minus x. Now, a and b are what are considered arbitrary constants. So we need a particular solution. We need some boundary conditions to fully solve the equation. But that's literally it. That is just the general solution. That's literally it. So that was one example out of three. I'll show you the other two now. Okay. Okay, we have another example. Let's say that d2y with dx squared minus 6 dy by dx plus 9y equals 0. Okay? So, when we solve this, what we will get is m squared minus 6m plus 9 equals 0. And then when we solve this, as you notice, this is not a difference of two squares, but what this is a, I forgot what it's called now. Yeah, a repeated root, sorry. This is what's known as a repeated root. So, when we solve this, we will just get m is equal to 3. Therefore, our differential equation, our general solution to this equation is equal to y equals a plus bx e to the power of 3x. That is our general solution. So that's our second one. As you notice, these two are different. You're probably thinking, two different solutions. So this is a repeated root, so this must have a different general solution. And then this has two roots, two real roots, and therefore there's a different general solution with two arbitrary constants. Well, but all have arbitrary constants, but still. Now we're going to go on to the third example. I can get rid of that now. d2y by dx squared minus 6dy by dx plus 34y equals 0. We're going to solve it as normal. We're going to set dy by dx squared is equal to m squared, dy by dx as m, and just 34y as a constant. So we're going to say that m squared minus 6m plus 34 equals 0. This is what you have to do at any point. It doesn't matter if you put m, you can put lambda, mu, you can put whatever you want. As long as later on when we do non-homogeneous, you don't get them mixed up. So, I can't be bothered to, well, you can use quadratic equations, so we will. So we have 6x, 6 plus or minus 36, 4, 34, 1 all over 2. When we solve this, we will get non-real roots. So we will get two individual complex roots. So we will get that m is plus or minus 5i, where I is a complex an imaginary number. Okay, you're probably thinking, well, okay, we've got complex roots, so what's the general solution? Well, my friend, the general solution to this is equal to y is equal to e to the 3x, all in brackets, a cos 5x plus b sine 5x. And that is our general solution. So, we have three different individual cases for when we need to use a general solution. So, in our first example, we have real roots. So, our general equation will always be ae to the power of, I'm going to call this mu x, and be to the power of nu x, where mu and nu are real roots. Okay, we have our second example. We have a repeated root. So our general solution is y is equal to a plus bx e to the power of mu x, where mu is the repeated root. And we have our third case from our third example, complex roots. Okay, so our general solution is y is equal to e to the power of mu x, a cos nu x plus b sine mu x. Those are the three cases that you must remember. Otherwise, you are going to be screwed on which one it is. It's honestly easy to distinguish, which ones are which. So I'll just give you just a few exercises to do, and then we'll move on to non-homogeneous differential equations. Yeah, I'll give you these 4 exercises to do, and then obviously if you want to challenge yourself to more homogeneous differential equations, be my guest. Head over to a textbook or whatever, and then you'll be fine. Non-homogeneous differential equations are a bit more complex. A non-homogeneous differential equation is in the form of a d2y by dx squared plus b dy by dx plus cy equals a function. So that's what we mean by a non-homogeneous. So now there are 5 or more separate cases to consider. I'll show you how to solve this, and then you'll be fine. So I'm going to have one differential equation with 5 different functions, and then you can see how they all differ using what's called a particular integral. So our equation is d2y by dx squared minus 5 dy by dx plus 6y equals a function. Okay? So we're going to solve it like a homogeneous equation. This is what you always have to do first. So we're going to say that m squared minus 5m plus 6 equals 0. That's what we're going to do first. You always have to do this. Now, we're going to factor, if possible. So we're going to say that m, well, what does this go to? M plus 6, m minus 1. Pretty sure? Yeah. No. No. Not sure if this goes to a complex. 5 plus minus square root of 25 minus 4, 6, 1 over 2. This goes to plus minus a half. So this is, so it's either, so m is equal to either 3, oh yeah, 3 and, of course, 3 minus 3 and minus, no, yeah, minus 3 and minus 2. That's what our solutions will be. So we solve it like a general solution. So we're going to say that y is equal to ae to the minus 3x plus be to the minus 2x. That is our current general solution, but what we need is a particular integral. This bit is known as the complementary function. I don't know if I spelled it right. And then this is our particular integral. The thing is, we don't actually integrate it. That's the thing. So, remember our equation. We have 5 different cases to consider. So, we're going to consider the first case, where f of x is equal to 3. So we're going to say that d2y by dx squared minus 5 dy by dx plus 6y is equal to 3. That's what we're saying. So what we're going to do, we're going to say let y equal lambda. So we're going to say that dy by dx equals 0, oh sorry, equals 1, no sorry, this is a constant, lambda is a constant, so dy by dx is equal to 0, which is also equal to d2y by dx squared. So now what we're going to do, we're going to substitute all these values into the original differential equation. So we're going to say that lambda minus 5, 0 plus 6, 0 is, that 0 minus 5, 0 plus 6 lambda is equal to 3. So 6 lambda is equal to 3, therefore lambda is equal to a half. Therefore, our general solution is equal to y is equal to ae to the minus 3x plus be to the minus 2x plus a half. That is now our general solution. So we have our complementary function here, and then we have our particular integral here. I hope that's helping so far. If not, just rerun it or refer to a textbook or whatever. Okay? Okay. So we have our second case where f of x is equal to 2x. Okay? So now, we've already solved our, we can say that m squared, so let's get our differential equation back up. So we have d2y by dx squared minus 5 dy by dx plus 6y equals f of x. And our complementary function is equal to ae to the minus 3x plus be to the minus 2x. That's our complementary function. Sorry, y is equal to. Okay? I hope this is not rushed because I don't want to rush things. So now what we're going to do is we're going to let y equal to lambda x plus mu. The reason we're considering this case is because we're considering a 2x here. So it's got 2x plus a constant, but there is no constant, but we still have to apply this mu here. So when we're going to when we differentiate this, we're going to say that dy by dx is equal to lambda, and d2y by dx squared is equal to 0 because lambda is a constant. Now we substitute this back into the differential equation. So we're going to say that 0 minus 5 lambda plus 6 lambda x plus mu equals 2x. Okay? So we have minus 5 lambda plus 6 lambda x plus 6 mu. Okay? Now, what we are going to say is we are going to compare functions. We're going to compare coefficients, So we're going to say that we're going to compare x. So we have our x's on one side and x's on the other. So we're going to say that 6 lambda is equal to 2. Okay? So then lambda is equal to a third. Now what we're going to do is we're going to sort this equation out. We're going to say that compare coefficients. So here we just compared all of our x terms. So that 6 lambda is equal to 2. That's what we're doing. This time we are comparing the coefficients. So therefore, we can say that 6 mu is equal to 5 lambda. And when we say that lambda is equal to a third, we will get that 6 mu is equal to 5 over 3. Therefore, mu is equal to 5 over 18. Therefore, our general solution is equal to y is equal to ae to the minus 3x plus be to the minus 2x plus a third x plus 5 over 18. So we substitute our mu and our lambda and our mu back into the differential equation to form our general solution. I hope this is really helping because this is only 2 out of 5 so far. Okay, let's consider case 3. where f of x is equal to 3x squared. Okay? So we are going to let y equal to lambda x squared plus mu x plus nu. Nu is a constant. So when we differentiate this, we will get 2 lambda x plus mu. And when we differentiate again, we will just get 2 lambda. We're going to put it back into the differential equation. So we are going to say that 2 lambda minus, from putting it back into this, so substituting again. So we're going to say that 2 lambda minus 10 lambda x plus, minus 5 mu plus 6 lambda x squared, I'm trying to save as much space as possible, plus 6 mu x plus 6 nu is equal to 3x squared. Trying to fit as much as possible if I can. Okay, now what we're going to do is that we're going to compare our x squared terms. So when we compare our x squareds, we will get that 6 lambda is equal to 3. So therefore, lambda is equal to 1/2. We're going to compare our x terms. So we're going to say that minus 10 lambda plus 6 mu is equal to 0. So therefore we can say that 6 mu is equal to 10 lambda. Now what we're going to do is compare coefficients. So we're comparing each term where necessary. So when we compare our coefficients, we're going to put that 2 lambda minus 5 mu plus 6 nu is equal to 0. Now, what we have here is that we've already found lambda. Lambda is equal to 1/2. So what we can do now is that we can substitute this into this to find mu, and therefore we can find nu. So 6 mu is equal to 5. Therefore, mu is equal to 5/6. Now we can substitute it back into the coefficients. So we can say that 1 minus 5/6, 25/6, equals minus 6 nu. And when we solve this, we will get nu as 19/36. That is what we will get. And therefore, our general solution is equal to y is equal to ae to the minus 3x plus be to the minus 2x plus 1/2 x squared plus 5/6 mu, 5/6x plus 19/36. I really do hope this is helping. I know I've said it on every case so far. Okay, so we're more than halfway through. Let's just bomb through it if we can. Okay, so this time now we have our fourth case where f of x is equal to e to the x. And this also applies if f of x is equal, we'll consider that case. This also applies if it's equal to e to the minus x or e to the 2x. E to the 2x. That's what we'll do. Okay? So, I'm going to write it all again. So d2y by dx squared minus 5dy by dx plus 6y equals fx. And our complementary function is equal to y equals a to the minus 3x plus b e to the minus 2x. Just as a reminder. So, our fourth case when f of x is equal to e to the x. So, we're going to let y equal lambda e to the x. So, we're going to say that dy by dx is equal to also lambda to the ex. And this is also the case for d2y by dx squared. So when we substitute it all back in, we will get that lambda e to the x minus 5 lambda e to the x plus 6 lambda e to the x equals e to the x. Okay? So putting it all together, we can say that 2 lambda e to the x is equal to e to the x. They will cancel, therefore lambda will equal 1/2. Therefore, our general solution is equal to y equal ae to the minus 3x plus be to the minus 2x plus 1/2 e to the x. Now, there's also one thing that I want to note as well. If you have a if a function f of x if a function of f of x of e to the x has the same power. Yeah. No. Anyway, what was I saying? If a function f of x has the same power of any sort in the complementary function, just listen to what I'm saying. If a function that's equal to this differential equation has the same power of the complementary function, we set that particular integral as lambda x e to mu x. That's what we do. So we put an x term in there just to not make things easier, but to make things more easier. Okay, now we're going to consider the fifth and final case. Case 5, where f of x is equal to 13 sine 3x. Okay, so after doing all that, we're going to let y equal lambda sine 3x plus mu cos 3x. That's what we're going to do. So, dy by dx is equal to 3 lambda cos 3x minus 3 mu sine 3x. Then d2y by dx squared is equal to minus 9 lambda sine 3x minus 9 mu cos 3x. Okay, so when we substitute it all in, we will get that minus 9 lambda sine 3x minus 9 mu cos 3x, this is a long one, minus 5, I'm going to simplify this, 15 mu cos 3x plus 15 mu sine 3x plus 6 lambda sine 3x plus 6 mu cos 3x is all equal to 13 sine 3x. So we're going to simplify it slightly because that, so 6 minus 9, so we're going to get minus 3 lambda sine 3x minus 3 mu cos 3x minus 15 lambda cos 3x plus 15 mu sine 3x equals 13 sine 3x. This one's a long one, I have to admit. So when we sort all of this out, we're going to compare sine 3x. So what we get is that we get minus 3 lambda plus 15 mu is equal to 13. That's not a b. And then we're going to compare cos 3x. So when we compare cos 3x, we will get minus 3 mu minus 15 lambda equals 0. That's what we will get. So when we sort this out, we have two different equations. We have, what was I going to say now? Yeah, sorry. We have two different simultaneous equations. What we can do straight away is that we can sort of solve this. So we're going to say that mu is equal to minus 5 lambda. Therefore, we can substitute lambda into this equation. So what we will get here is 15... minus 3 lambda plus, so mu, blah, 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 15 times 5, 75. Can't even struggle to say that. Minus 75 lambda equals 13. So what we'll get is that minus 78 lambda equals 13. Therefore, lambda will equal minus a sixth. I hope. That's what my book says. And therefore, what we can get is that mu is equal to 5 over 6. Oh, yeah, that seems right. Okay. Therefore, our general solution for that fifth case is our general solution for the fifth case is y equals ae to the minus 3x plus be to the minus 2x plus, minus a sixth sine 3x plus 5 over 6 cos 3x. That is the general solution for the fifth case. So, in a summary, these are the steps to follow. Set d2y, a d2y by dx squared plus b dy by dx plus cy equal to 0. Then solve, then find the complementary function. Then set up the particular integral, didn't mean to put a capital letter there, so set up the particular integral, solve where necessary, i.e. your constants, and then 4 is that your general solution is equal to y is equal to your complementary function plus your particular integral. That is how to solve the general solution of a second order differential equation in 5 different individual cases. So as a preference, your particular integrals, if, so a form of f of x, so if it's a constant, so p, q, and r are constants, this little symbol means a set of, for example. So if it's in the form p, your particular integral is lambda, is only lambda, so these are just constants. If it's px plus q, then your particular integral is lambda x plus mu. If it's the form of a quadratic, it's pqx squared plus pqx plus r. So it'll be lambda x squared plus mu x plus nu. Then if it's a form of pe to the power of kx, your general solution will be lambda e to the kx, or lambda x to the e to the kx, where if complementary function already has e to the kx. So basically those are the same, you have to put an x in front of it. So, and the last thing is if it's in the form of p cos, what does it say, omega x plus q sine omega x, then your particular integral will be in the form of lambda cos omega x plus, I've forgotten now. Sorry, yeah, just lost train of thought. Plus mu sine omega x. Those are just some preferences in your particular integrals. This is a really complex topic and you really have to understand and remember every step, all the particular integrals. I know it's not ideal, but it is really important that you must know. I'll just put some questions or whatever on. Let's have a look. Okay, so here are some questions to do. Pause the video, and then obviously if you already have a book, then by all means solve. If not, then what I'll do is I'll link the solutions for each exercise in the description below. Okay, so that's one part, and then here is another part. There's another part for you. So pause the video and then remember, if you wish to go on the challenge, by all means. So there you go. That is finding the general solution of each differential equation. It's been fun for the last 40 odd minutes or so, but thank you for watching. Please give the video a like and please subscribe for more content as well. I hope you really enjoyed, well, not so much enjoyed it, but I hope you relatively enjoyed it. and I hope you have a good day. Thank you very much for watching. Thanks.